Today, we can see some of the general properties of the compounds of alkali metals, oxides and hydroxides of alkali metals. Oxides and hydroxides of alkali metals are basic in nature. When they dissolve in water, forms alkali solutions. Sodium hydroxide, potassium hydroxide, examples. And you may be familiar with the sodium hydroxide, it has no color. The oxides and peroxides are colorless when pure. But the superoxides are yellow or orange in color. The superoxides are also paramagnetic, that we discussed in the 4th chapter. Superoxides are paramagnetic because of the presence of unpaired electrons. Sodium peroxide is widely used as an oxidizing agent. Sodium peroxide that when dissolves in acids forms hydrogen peroxide. And you know, peroxides can release nascent oxygen, so it can act as an oxidizing agent. Next one is halides. Sodium chloride is an example for halides of alkali metals. The alkali metal halides, MX, X means halogen, fluorine, chlorine, bromine, iodine, are all high melting, colorless crystalline solids. The melting and boiling points always follow the trend: fluorides greater than chlorides, greater than bromide, greater than iodide. HF bond, that is very strong bond. And you know, there is hydrogen bond between hydrogen and hydrogen atom of one molecule and fluorine atom of the other molecule. And because of this hydrogen bond, the melting point is very high in the case of hydrogen fluoride. And as we move to hydrogen chloride, there is no hydrogen bond, only dipole-dipole interactions are present. Similar to the case of bromide and iodide. So fluoride is having highest melting point. All these halides are soluble in water. The low solubility of lithium fluoride in water is due to its high lattice enthalpy, whereas the low solubility of cesium iodide is due to smaller hydration enthalpy of its two ions. Some points that you have to notice. Lithium fluoride solubility is very low. The reason, high lattice enthalpy. Cesium iodide solubility is low. What is the reason? Smaller hydration enthalpy of CS plus and I minus. That is the reason. Now salts of oxoacid, which are the oxoacids. HNO3 is an example. H2SO4 another example. So OH groups, acids in which OH groups are present. Oxoacids are those in which the acidic proton is on a hydroxyl group, OH group. Hydroxyl means OH group. The alkali metals form salts with all the oxoacids. Alkali metals will react with all the oxoacids, with nitric acid, sodium nitrate, with the sulfuric acid, sodium sulfate, with the phosphoric acid, sodium phosphate. Alkali metals will react with all oxoacids. Anomalous properties of lithium. We already mentioned the first element of each group has a lot of differences from other elements of the group. It is the anomalous property. And this property is due to the small size, high ionization enthalpy, higher electronegativity, and absence of d orbitals in the first element of each group. So lithium has a lot of difference from other members of the group. We can see that lithium is much harder. Its melting point and boiling point are higher than the other alkali metals. Lithium is least reactive, but the strongest reducing agent among all the alkali metals. The electrode potential is more for lithium. Therefore, it is the strongest reducing agent. Electrode potential more means the negative value is more for lithium. But lithium is least reactive. Strongest reducing agent, but lithium is least reactive. LiCl is deliquescent. What is meant by deliquescent? Absorb water from the atmosphere or moisture from the atmosphere. It absorbs water, then slowly changes to the solution. LiCl is deliquescent crystalline hydrate. LiCl2H2, whereas other alkali metal chlorides do not form hydrates. NaCl is not forming any hydrate, and that is not deliquescent. If there is any impurity, sodium chloride will be deliquescent. Impurities such as magnesium chloride or calcium chloride, if present, it will absorb water. In the pure state, sodium chloride is not deliquescent. Lithium hydrogen carbonate is not obtained in the solid form, while all other elements form solid hydrogen carbonates, bicarbonates. That is, it is very difficult to get lithium bicarbonate in the solid form. But all other bicarbonates can be prepared. We will get it in the solid form also. Now, diagonal relationship. Lithium has diagonal relationship with magnesium. So what are the similarities between lithium and magnesium? Or what is the diagonal relationship between lithium and magnesium? The reasons we already discussed in the third chapter, reasons for the diagonal relationship. Charge to radius ratio same, almost the same. Atomic radii, almost same electronegativities. All these things we discussed earlier. Lithium and magnesium react solely with water, very slow reaction, but other alkali metals, vigorous reaction with water. Their oxides and hydroxide are much less soluble, and their hydroxides decompose on heating. Actually, sodium hydroxide or potassium hydroxide, rubido or cesium hydroxide will not decompose on heating. But lithium hydroxide decomposes on heating as lithium oxide and hydrogen. In the case of magnesium also, that will happen. Hydroxide decomposes and solubility is less in water. Both form a nitride when treated with air. Lithium nitride, Li3N and Mg3N2, magnesium nitride. But other alkali metals has no reaction with nitrogen in the atmosphere. Sodium has no reaction with the nitrogen at any temperature. But lithium form nitride like magnesium. The carbonates of lithium and magnesium decompose easily on heating to form the oxides and carbon dioxide. Alkali metal carbonates are stable that will not decompose on heating. But in the case of lithium, the carbonate decomposes like magnesium carbonate. Another similarity between lithium and magnesium. Both lithium chloride and magnesium chloride are deliquescent. I told you other alkali metal halides are not deliquescent. Now, some important compounds of sodium. The first one is sodium carbonate. It is known as washing soda, sodium carbonate. Na2CO3, 10H2O, washing soda. Na2CO3 without water of crystallization. Simple Na2CO3, that is dry ash. That is known as dry ash. Sodium carbonate is known as washing soda. Okay, sodium carbonate is generally prepared by Solvay process. What is the name of the process for the preparation of sodium carbonate? Solvay process. In Solvay process, sodium chloride solution is saturated with NH3. Means NH3 gas will pass into sodium chloride solution, brine solution. After saturating it with NH3, CO2 is passed into this solution. Then what are the reactions taking place there? We can see the reactions. NH3 react with the carbon dioxide to form ammonium carbonate first. Ammonium carbonate react with again more amount of CO2 to form ammonium bicarbonate, NH4HCO3. This NH4HCO3 react with the NaCl to form NaHCO3, sodium bicarbonate. And we have to prepare sodium carbonate. Here what is obtained? Sodium bicarbonate. Now how will you convert it into sodium carbonate? Sodium hydrogen carbonate or sodium bicarbonate crystals separate because of comparatively lower solubility of sodium bicarbonate. These are heated to give sodium carbonate. The sodium bicarbonate on strong heating gives sodium carbonate. In this process, advantage is taken of the low solubility of sodium hydrogen carbonate. Comparatively lower solubility helps the precipitation of sodium bicarbonate. We can precipitate it and separate. Then on strong heating, sodium bicarbonate changes to sodium carbonate. It is the reaction. Sodium bicarbonate on heating is Na2CO3 plus CO2 plus H2O. Sodium carbonate is obtained. Here, saturated with NH3, we already mentioned. After the process in the reaction, you can see ammonium chloride is formed. From this ammonium chloride, we can regenerate ammonia. How can you regenerate ammonia from an ammonium salt? By treating it with an alkali. So here, which alkali can be used? Calcium hydroxide can be used. In this process, NH3 is recovered when the solution containing NH4Cl is treated with calcium hydroxide. Calcium chloride obtained as a byproduct. Calcium chloride will be a byproduct in that reaction. And this calcium hydroxide we can produce from calcium carbonate. When calcium carbonate is heated, we'll get calcium oxide and carbon dioxide. That carbon dioxide can be used for the production of sodium bicarbonate. We have to pass carbon dioxide to ammoniated brine solution, isn't it? So we'll get calcium oxide. That calcium oxide, when mixed with water, produces calcium hydroxide. So NH4Cl plus calcium hydroxide gives NH3 plus calcium chloride plus H2O. Solvay process cannot be extended to the manufacture of potassium carbonate. Why? You can expect such a question. Because potassium hydrogen carbonate is too soluble to be precipitated by the addition of ammonium hydrogen carbonate to a saturated solution of potassium chloride. The solubility of potassium bicarbonate is comparatively higher. Therefore, it is very difficult to precipitate potassium bicarbonate. So we cannot use Solvay process for the production of potassium carbonate because potassium bicarbonate is more soluble. In the Solvay process, we will precipitate the compound as bicarbonate, then on strong heating, form sodium carbonate. In the case of washing soda, Na2CO3, 10H2 on strong heating, that means at above 373 Kelvin, it completely removes water of crystallization and becomes anhydrous. Then it will change to a white powder called soda ash. Oh, sorry, not a dry ash, soda ash. On completely dehydrates and anhydrous sodium carbonate is known as soda ash. Earlier I mentioned it as dry ash, not dry ash, soda ash. Anhydrous sodium carbonate is known as soda ash. And Na2CO3 10H2O is known as washing soda. Anhydrous sodium carbonate is known as soda ash. Now the uses of sodium carbonate. It is used in water softening, removal of hardness, permanent hardness, already we mentioned, laundering and cleaning. It is used in the manufacture of glass, soap, borax, and caustic soda. It is used in paper, paints, and textile industries. It is an important laboratory reagent both in qualitative and quantitative analysis because it is an important laboratory reagent. Now, sodium chloride, NaCl, all of you are familiar with the sodium chloride. You know the uses of sodium chloride, a preservative, and to give taste to our food material, food items, and sodium chloride that is using for the production of just now we saw it. Sodium carbonate is produced from sodium chloride. Sodium hydroxide is produced from sodium chloride for the production of different compound sodium chloride is using. The most abundant source of sodium is sodium chloride. And the most abundant source of sodium chloride is seawater, which contains 2.7 to 2.9% by mass of the salt. To obtain pure sodium chloride, the crude salt is dissolved in minimum amount of water and filtered to remove insoluble impurities. The solution is then saturated with the hydrogen chloride gas. Crystals of pure sodium chloride separate salt. By the evaporation of seawater, we will get sodium chloride, but that is highly contaminated. A lot of impurities are present in it. Therefore, the solidified sodium chloride first dissolves in pure water. Insoluble impurities filtered and removed. Then further purification is done by the crystallization of sodium chloride from that solution by saturation with the hydrogen chloride gas. Then it will precipitate. Sodium chloride will precipitate. Sodium hydroxide, caustic soda, NaOH. It is an important compound of sodium hydroxide. We require it for many applications. Sodium hydroxide is prepared by the electrolysis of sodium chloride solution in a special cell known as Kellner cell. What is the name of the electrolytic cell for the production of sodium hydroxide? Kellner cell. A brine solution means sodium chloride solution is electrolyzed using a mercury cathode. In Kellner cell, a mercury cathode is present. You know, mercury is a liquid and it will be a liquid layer at the bottom. And carbon anode. Sodium metal discharged at the cathode combines with the mercury to form sodium amalgam. Chlorine gas is evolved at the anode. And the reaction Na++ electron gives Na, and that Na dissolves in mercury to form sodium amalgam. Cl- gives half Cl2+ electron. The amalgam is treated with the water to give sodium hydroxide and hydrogen gas. So this sodium amalgam formed. Sodium amalgam, sodium will be precipitated at mercury, and that two will combine actually a formation of solution that is known as sodium amalgam. That will move to the middle compartment. And in the middle compartment, it will combine with the H2O. Actually, in gas and kernel cell, there are three, an outer compartment and an inner compartment. So in the outer compartment, the sodium will form. And that moves to the middle compartment. There it combines with the water and liberates sodium hydrogen gas. It liberates hydrogen gas. At the same time, sodium will change to sodium hydroxide. Sodium amalgam plus H2O gives NaOH plus Hg plus H2. Hydrogen gas will liberate. So what are the two products? Chlorine and hydrogen are the products, byproducts in Kastner-Kellner cell, and sodium hydroxide will be produced. Sodium hydroxide is the major product. H2 and Cl2 are the byproducts. And the uses of sodium hydroxide. It is used in the manufacture of soap, paper, artificial silk, and number of chemicals. In petroleum refining, in the purification of bauxite, in the textile industries for mercerizing cotton fabrics, for the preparation of pure fats and oils, and as a laboratory reagent. Okay, you have to remember 2 or 3 uses. The next one is sodium hydrogen carbonate, baking soda, NaHCO3. Have to remember the commercial names. Baking soda, NaHCO3, baking soda. NaOH, caustic soda. Sodium carbonate, there are 2 names, Na2CO3, 10H2O, washing soda, and Na2CO3, soda ash. You have to remember the names. Sodium hydrogen carbonate is known as baking soda because it decomposes on heating to generate bubbles of carbon dioxide. So in preparation of cakes, sodium bicarbonate is using to make it soft and porous. Sodium hydrogen carbonate is a mild antiseptic for skin infections. It is used in the fire extinguishers. And the preparation of sodium hydrogen carbonate, we can prepare it in 2 ways. You know, in the solvent process, we'll get sodium bicarbonate first. Suppose you in the laboratory you have only sodium carbonate, then it is possible to prepare sodium bicarbonate from sodium carbonate by passing carbon dioxide to sodium carbonate in the solution of sodium carbonate in water. When you pass carbon dioxide to the solution of sodium carbonate, that will change it to sodium bicarbonate. That way also we can prepare. Now, biological importance of sodium and potassium. You know, sodium and potassium are biologically very important. The sodium-potassium ratio is also very important. Hypertension, pressure, that is related to the concentration of sodium-potassium ions. All these things known to you. These ions participate in the transmission of nerve signals, in regulating the flow of water across cell membranes, and in the transport of sugar and amino acids into cell. These are the biologically important. Sodium and potassium, although so similar chemically, differ quantitatively in their ability to penetrate cell membranes. Sodium, potassium, almost same behavior, but their abilities to penetrate the cell membrane is different. In their transport mechanism and in their efficiency to activate enzymes, not only to penetrate cell, but in their transport mechanism and in their efficiency to activate enzymes. In all these properties, they are different. Potassium ions are the most abundant cations within cell fluids, whereas they activate many enzymes, participate in the oxidation of glucose to produce ATP, and with the sodium are responsible for the transmission of nerve signals. So I wrote here only some important applications. So you should know what are the biological importance of sodium and potassium. And next we have to study the alkaline earth metals. In the next class we can